Hi everybody, I'm Dr. Munchie and today we're going to cover stress and strain. Let's start by going over an outline of today's video. We're going to start with a stress review, then go over a strain review, talk about the connection between stress and strain, and then we're going to go over a brief example. So let's get started by going over a review of stress. Let's consider this person who's lying on a bed of nails, as you can see in this cartoon picture. Why is it that people who do this, which by the way some people do this in real life, don't experience pain when they're lying on a bed of nails? Well, imagine if there were 2 nails there instead of several. Well, the nails would then puncture the person, right? Let's increase the number of nails from 2 nails to 20 nails. You'd feel less pain, or some pain, but less than if there were 2. If we go to 200 and then 2,000, we'd be experiencing significantly less and less pain as you increase the number of nails. So, what is this relationship between the number of nails and the level of pain that we experience? And that can be defined by understanding stress. So stress can be defined as the force per unit area. And let's kind of think about this in terms of this person lying on the bed of nails again. So let's just say this person weighs 200 pounds, right? Pounds are a force, so the force would be 200 pounds here. And let's consider those 2 nails again, which we had said earlier would puncture the person. Why would they puncture the person? So we're going to take the 200-pound weight, which is a force, and divide it by the 2 nails, and that means we get 100 pounds per nail, which is really high. That means we have 100 pounds of force per each nail that person is sitting on. If we increase the number now to 200 nails, we have the same weight, 200 pounds, divided by 200 nails. So now this 200-pound person is spread across 200 nails, so more surface area, and we decrease from 100 pounds per nail to only 1 pound of force per nail. So you see, 100 pounds per nail is much more force per each nail versus only 1 pound per nail. And this is why we would experience less pain as we increase the number of nails that we're sitting on. Okay. Now, let's discuss this in terms of a concept. So we want to see, what is this concept of stress? And really what stress defines is, how do we distribute force over a certain area? Or what is this distribution of force over a certain area? Okay. So I'm going to write this out in terms of a question for you. How has a force been distributed throughout or over area? Okay. Let's continue, and let's now talk about some different types of stress. So we have 2 different kinds of stress we're going to go over today. The first is called normal stress, and the second is called shear stress. Normal stress, we use the Greek letter sigma. So that little Greek letter you see on the screen is called sigma. And for shear stress, we use the Greek letter tau. Okay. We have a diagram here that shows sigma and tau, and I'll talk more about this in the next coming slides, but sigma basically acts perpendicular to the face of the element. So we have the face of the element here, which is this square. Let me go back a little bit. Right, and you can see that sigma acts perpendicular to the face of the element, and then we have the shear stress tau, which acts parallel to the face of the element. And that's the difference between shear stress and normal stress, which we're going to go over in a little more detail in the upcoming slides. Okay. All right. So within normal and shear stress, we have a few different types of stresses that we're going to go over. So not only do we have normal and shear, but we can cause normal and shear stress from different types of stress. Okay. So this is kind of a breakdown of what we're going to go over. In the category of normal stress, we have axial and bending, and in the category of shear stress, we have average, transverse, and torsion. So let's start by talking about axial stress, or how we cause normal stress through axial force. So let's consider a bar element, and I've drawn a bar here on the screen for you, and let's say that we pull this bar. Okay, and if we pull this bar, a couple times to get a straight line, but we're pulling this bar, that means this bar is in tension. We can also push this bar, which means it's in compression, but I'm just going to show you one example here as if we're pulling it, which means it's being pulled in tension. Okay. So when we pull on this bar with force F, this is axial force, and this axial force leads to normal stress. The second type the second basically category of normal stress that we have is due to bending. So let's say we have another bar and we apply a force F on the bar. The bar would deform in this shape here that's on the screen, right? It would have this curvature. And we'd have the top of that bar experiencing compression and the bottom experiences tension. Why does the top experience compression and the bottom experiences tension? Because you can see the top of the member is actually getting shorter while the bottom of the member is getting longer. So when the bottom gets longer, it's in tension. When the top gets shorter, it's in compression. And this action of bending also contributes to normal stress. Now moving on, we have shear stress, and we're going to talk about average shear stress first. And to do that, let's consider two bars that are joined together by a bolt. And I'm going to draw the bolt here for you as well. So we have the bolt that's joining two bars, and this is going to be pulling on each bar, right, with some force, V. I'm going to use V to denote the shear stress. And this is single shear. Why is it single shear? Because we only have one plane that's connecting those elements, right? And I'm going to show you in pink here. So that's just one plane, which means we have single shear. We had two planes, we have double shear. Okay, so in this problem, we have single shear, and this action leads to shear stress. Okay, the next type of shear stress we're going to go over is called transverse. Again, I'm going to draw this bar element for you, and this is when we have a force on top of that bar element, perpendicular to the bar element, right? This also causes transverse shear stress to occur in the member. Okay, I'm going to draw a little square there for you to show you where that occurs, but basically those are the types of shear stress we have, and we have the last one, which is due to torsion. So I have a picture on here. This is easier for me to put it here than to draw it. So we have this bar, and you can think of this bar kind of like a steering wheel. So you would push it down on one side, up on one side, and you'd get this twisting motion. And this twisting motion is torsion, and this torsional twisting motion contributes also to shear stress in your element. Okay, so now let's move on, and we're going to go over strain. We denote strain with this little E-looking Greek letter, which we call epsilon, and that is equal to delta L over L. What is delta L? What is L? Delta L is the change in length of the member, and L is the original length of the member. So I'm going to draw here for you a bar, and let's say it's fixed to a wall that doesn't move, and we pull on this bar with some force F. We could also push on it, but we're pulling, let's say in this case. If you're pulling on this bar, and it has an original length of L, it's going to deform by some little delta L, right? This little red portion is going to pull by that much, and that's some change in the length of the member, right? So that little delta L divided by the total L, that gives us the strain in that element. Okay, we can have tensile strain or compressive strain, right? This example is tensile strain. How do we make this compressive strain? Instead of pulling on the element, we push on the element. Instead of it getting longer, it would get shorter. So tensile strain means we're pulling, it's an increase in length. Compressive strain means we're pushing, decrease in length. Okay, so both of these can be tensile or compressive depending on if you pull or you push. Now, let's go over the relationship between stress and strain briefly here. You'll learn more about this in the video where we go over the stress-strain curve. But for now, let's talk about the relationship in terms of Hooke's law. One thing to remember is Hooke's law is only valid in the linear elastic portion of the stress-strain curve. So let's consider that we are in that linear elastic portion. We would have stress, sigma, is equal to the modulus of elasticity, which is also called Young's modulus. It's the same thing. We use the letter E to denote that, multiplied by epsilon, which is the strain in the element. So stress is equal to E, modulus of elasticity, times the strain. Right? And this is just a linear function, and you'll learn more about that again when we go over the stress-strain diagram. Okay. Now I'm just going to put all of these definitions here for you, and then let's consider now units. So let's say we're talking about normal stress and strain. We have normal stress sigma is equal to force over area. So let's just figure out what these units would look like if we're in US customary and SI. US customary, we'd have pounds and inches so pounds for force, inches squared for area, and SI we'd have newtons and meters squared for force and area respectively. If we're in US customary, that means we have pounds divided by inches squared, or PSI, right? Pounds per square inch. And if we're in SI units, we would have newtons per meter squared, and this is actually just a Pascal, which we abbreviate as PA. So either one of these units are appropriate when we're talking about stress, okay? When we're talking about strain, we'd have delta L over L. Change in length is in inches, or measurement, and L is in inches. So technically this is unitless, but we would still use inches per inch or millimeter per millimeter when we're kind of going over this problem. So let's now put all of this information together and try out an example. I'm going to draw a bar with a fixed support, and I'm going to pull on that bar, right? So this is tension. I'm going to pull on that bar with 20 kips of force, okay? What is a kip? One kip is equal to 1,000 pounds. I'm going to put that on the screen for you shortly. Right now, I'm going to define the original length of the bar, which is 10 feet. Okay? And again, I'm going to put here 1 kip is equal to 1,000 pounds, just in case you didn't know that conversion. Okay. Now, let's try to figure out, we have point A, which is the fixed point. We have point B, which is where we're applying that 20 kip force. And also, we have the cross-section of the element, which is a square, and the area is given as 2 inches squared. Okay, we need one more piece of information to solve for this. So, the modulus of elasticity is equal to 29,000 KSI, which is kips per inches squared. Remember, 1 kip is 1,000 pounds. Now we have all of the information that we need to solve for this problem. And remember, for this problem, we're going to consider that we are in the linear elastic range, so that Hooke's law does apply. Okay, let's start by figuring out the stress. So stress is equal to, or sigma is equal to force divided by the unit area. Easy, right? We have the force, 20 kips. We have the area, 2 inches squared. 20 divided by 2 is just 10 KSI. Done with that. Next, we're going to calculate the strain. So we know that strain, epsilon, is equal to delta L over L, but we don't really have delta L yet. So instead, we can use Hooke's law to find the strain, because we know this is in the linear elastic range, because I told you that's part of the problem statement, right? So 10 KSI, which we just solved for, is equal to 29,000 KSI, the modulus of elasticity, times the strain. And just real quick to go over, modulus of elasticity should be given to you because it's dependent on the type of material. So this is a common modulus of elasticity, or Young's modulus for steel. Okay, so that would be given to you, and it's dependent on the material type. Okay, back to our problem. This would give us 10 KSI divided by 29,000 KSI, which is 0.000345 inches per inch, which makes sense, right? Because KSI cancels out with KSI. So really that's unitless. We're just going to put the inches per inch there because this problem was given in US customary. Now we can calculate the change in length. So we have one more equation, epsilon is equal to delta L over L. Well, we have epsilon that we just solved for, and we have the original length L. So we can get 0.000345 is equal to delta L over 10 feet times 12 inches per foot. So make sure you're using the right units here. That 12 inches per foot is the unit conversion to go from the 10 feet to inches, because remember the 0.000345 is inches per inch, so just so everything is consistent, we use the same units. We multiply the 0.000345 times 10 times 12, and we get 0.00414 inches for our delta L. Okay? That is it for this video. I hope you learned something, and this material is a refresher for you. Try watching the next video if you want to learn more about stress or strain or a different topic.